Good afternoon, everyone. Our next session will start shortly.
Good afternoon.
Good afternoon,
Good
sir.
afternoon, sir.
Yeah, you are able to see the PPT.
Yes, sir. Yes, sir.
Okay,
It is clearly visible.
and you are able to hear me also.
Yes, sir.
Also, okay.
Okay, okay. So I'm ready.
Sir, should we start?
Yeah,
Just
you
wait
asked uh,
a few
Dr.
minutes. Let
Professor
us wait a
said.
few minutes. A few minutes.
Yeah, I mean,
Wait a few minutes.
Okay, sir. Okay, sir.
Just 4 minutes. Others will join. Hello,
yeah.
Professor A.
Good afternoon, sir. Good
Good
afternoon.
afternoon. Good afternoon.
There was some problem about internet here, and
Everywhere it is a problem.
yeah,
Everywhere.
so I'm not presenting from my PC, so I have switched over to laptop. So
Yes, sir.
sometimes, I mean, there might be some bandwidth related issues. So I'll switch off
Uh-huh.
my video after some time
Yeah, yeah.
so that we gain some
No
bandwidth.
problem, sir.
Let us please wait. It is only 2:31. So let us wait up to wait for another 3 to 4 minutes,
Okay, sir.
please. Yes.
I was present for the initial portion of Basu sir's lecture, but then later on, internet switched me off.
Okay.
Anyway, I had seen some of those presentations, sir, when you delivered invited talk for ITR Chandipur.
I will send you the PPT.
Yes, yes, I'll go through that, sir,
I
definitely.
will send you PPT. Certainly, I will do that.
Sir, you have started traveling now?
Beg your pardon? Yes.
Have you
Recently,
started?
I was at CD Pilani.
Okay,
I spent, actually, I went to Pankaj Dalela's,
okay.
P.K. Dalela, the director of, he is in Delhi.
Hmm.
I, I stayed there for 3 to 4 days. Yeah, his home. He's just like my home.
Okay.
And then from there, I was picked up by Siri Pilani.
Okay.
And from 6 to 12, I was there at Siri Pilani.
Oh, this month.
Yeah, this month.
Oh,
And
okay.
12th, I came back to Varanasi.
Okay.
Okay, so I started traveling a bit. You know,
Yeah.
I'm using wheelchair to be on safe side.
Right.
They take care, wheelchair if you take private plane.
Right.
So they take full care. So I don't have difficulty.
Okay.
And my wife also.
Anyway, Siri Pilani also is like second home for you.
Yes, it is my second, no doubt.
Yeah.
All are known to me.
Right.
Yes, present.
So sometimes we'll plan here
Yes,
also.
yes, yes. I think you have seen my article on Dr. Amarjit Singh. Did you see? Okay,
No,
it came in January 1, 2023, 22 to this is 22, 21 January, uh, quarterly magazine, quarterly newsletter of Siri Pilani.
okay.
So I wrote an article on Amarjit Singh.
Hmm.
So I
I
have,
think I scanned through that, sir. I have not
okay,
read
okay, okay.
fully. Yeah.
There you find
Yeah.
Dr. Amarjit Singh.
Right.
Yes. And this time Veda Society is being held at Bangalore, MTRDC. Veda
MTRD.
Society conference, yes, yes.
And
You
that
know
will
that?
be in the month of
January.
no,
January
January.
next
Okay,
year.
because December they have mega event of MapCon.
Mega event of?
That microwave antenna they have combined, sir, and then they called it MapCon now.
Okay, okay. Microwave antenna.
Yes, microwave and antenna international conference. So
Okay, I think Surinder Par will be there.
he is also there, but major role is being done by uh,
Antenna Society, MTT.
Antenna Society, and one Dr. Punit Misra is there.
Okay.
You met him in DIAT, sir, during Indian Antenna Week.
Yes,
Yeah.
Antenna Week. Yes,
Yes,
Antenna Week.
Punit Misra was there,
Mhm.
and I think he is doing PhD with Professor Guho.
And Calcutta,
Yes,
Devatosh
Debat.
was there. Yes.
Yeah, Professor Debatos Guha. He is scientist F, I believe, from ISAC Bangalore.
Okay. And Professor P.K. Saha is in Bangalore now.
Yeah. I mean,
I'm
once he
seeing it
had
is
sent email, so he is in Bangalore. I think his
Vidyamar.
daughter stays there. I think.
What about Anand Krishnan?
He was in US, and that time we had
No,
corresponded.
yes, he was in US. Yes, he is in
Right.
US. So
So,
he will not join here. Yes, must be yes. He is in US. Anand Krishnan was my classmate.
yes, you told
Anand
told
Krishnan,
us.
P.K. Saha, they
Yeah,
are my classmate.
yeah. And whenever you came to
Come to
DIIT,
yes, Anand Krishnan would come.
Dr. Anand Krishna used to
He
visit
would
us
come.
also,
Yes, that's right. Yes.
and he is very fluent in Bangla.
He can speak Bengali, yes,
Yeah,
because he was educated in Bengal,
right,
Calcutta.
right.
He cannot write Bengali, but he can speak Bengali.
Yeah. It's just opposite for me. I write later in Bangla, but I mix up word of Udiya and Bangla. So
But one thing, Uriya script is similar to, going towards Andhra, Telugu script.
yeah,
Uriya, actually, we can fluently understand. I have no
yes,
difficulty in understanding Uriya.
right, right.
But Uriya script, I cannot.
Yeah. That is
Bengali script is similar to Assami, Assam script.
Assamese and Hindi also.
Yes. But Uriya language-wise, it is close to Bengali. I mean,
Yes,
spoken
yes,
language, spoken
yeah,
language-wise.
right.
And I am now visiting. I visited. Yes, before going to Pilani, once I visited Bhubaneswar.
Oh, acha.
Bhubaneswar, my son is there.
Uh-huh.
Bhubaneswar, he is with Kolingo Institute.
Acha,
But not,
Kalinga Institute of Technology.
not technology. It is social science.
Acha, okay.
He's there. So I went to and stayed there for more than a month
Oh,
in Kalinga.
it's a nice place, sir.
Yeah. Deepta, can you hear me? Deepta,
Yes, sir.
could you start now?
Yes, sir.
Yeah,
Yes, sir. Obviously.
we can start. Yes. We can start now.
Welcome all again in the second session of first day's faculty development program on recent trends and advances in electronics. The speaker of this session is Professor Dr. K.P. Ray, sir. Professor Ray pursued M.Tech in microwave electronics from University of Delhi and PhD from Department of Electrical Engineering, IIT Bombay. Presently, he is a professor, Director School of Radar Technology, and head of the Department of Electronics Engineering, Defense Institute of Advanced Technology, DRDO, Pune. Prior to joining DIIT in 2016, he was the program director of Samir, Mumbai, wherein he joined Samir in 1985 and worked for over 31 years in the areas of electromagnetics, radars, RF, and microwave systems or components, and developed expertise in the design of antenna elements or arrays and high power RF or microwave sources for radar, scientific, and industrial applications. He has successfully executed over 55 projects sponsored by various government agencies and many industries. He was a guest faculty in Electrical Engineering Department at IIT Bombay, Goa Engineering College, University of Mumbai, and CEERI Pilani for postgraduate courses. He has guided over 10 PhD students, more than 130 MTech students, and evaluated more than 25 PhD theses. He has co-authored a book for Arctic House, USA, and published over 500 research papers in international or national journals and conference proceedings. He holds 3 patents, earned 10 transfer of technology for commercialization, and filed 5 patents. He has been associate editor of International Journal on RF and Microwave Computer Aided Engineering, John Bailey, IEEE, Defense Science Journal, and prolific reviewer of almost all journals in his field. He is a fellow of IEEE, a fellow of Vedas, a senior member of IEEE USA, and life member of Instrument Society of India and engineers of EMI or EMC Society of India. He received many awards, including most coveted IETE Ramlal Wadhwa Award 2018, IETE Ranjana Pal Memorial Award 2014, and several research paper awards. He has been listed as Indian researchers in Stanford University's top 2% most influential scientists list for the year 2020. Welcome, sir.
Yeah, so you are able to see my PPT properly?
Yes, sir.
Okay, and
You
then
can
also
see.
I'm audible to
Yes,
all
sir.
of you. Okay, so
Yes, sir.
at the outset, I would like to thank for very detailed introduction, and also I'm very grateful to
Yes, sir.
organizers of this program uh, uh, having allowed me to share some of my uh, research work, and through that some of the concepts we have picked up. So uh, I'm delighted to share some of the intricacy of this ultra wide technology, and also
Sir, there is
specifically.
no question of allowing.
Hello.
You can share whatever you want. You can share. You can show us. We will be able to progressed with your PPTs and whatever your work have done.
Yeah. So, that I'm happy to share, and some of the myths, those things which are there concerning these ultra wideband antennas, I thought I will try to clarify those things. It is widely understood that ultra wideband monopole antennas are microstrip antenna. This is how many papers they address this configuration, antenna configuration, but then that is not correct. So I deliberately chose this topic so that some of these things can be clarified. I am also very happy to deliver this talk in the presence of Professor Basu, who is like my guide, mentor, and then I have learned some of the aspects of electromagnetics from him. Though I was not a direct student, but then, like Eklavya, I picked up many things through his association. So I'm happy that he is also attending this lecture. Having said that, the basic outline of presentation are as follows. I mean, there will be brief introduction about the ultra-wideband systems, ultra-wideband antennas, in that both a planar, which is a three-dimensional ultra-wideband antennas, versus printed antenna, that will be compared. And then also we will directly go to printed monopole antenna. Both comparison we will try to see, and then finally some of the conclusion I would like to draw. Now, coming back to the basic introduction of ultra wideband technology, for which we require various ultra wideband systems. um, you know that in our country the frequency allocations is looked after by WPC, which is a planning wing under Ministry of Communication. And whenever we want to develop some new system, we have to apply for frequency clearance, and then after getting clearance, we go for the developing the system. And then day by day, you know that electromagnetic crowding is happening. Means various applications are being used, and then different frequencies are allocated for various applications. So there is lots of frequency jamming, I would say frequency crowding. And keeping that in mind, when some of the features are required for the system you are developing, uh, some those things will be best suited for certain frequency band. Like I'll give you example that if you want to study the precipitation of this cloud precipitation, or want to measure the raindrop size, you have to go for X band frequency. So like that, in communication or strategic application, some of the frequencies are must use. You cannot avoid using them. So keeping all these aspects, so once the frequency is allocated for one particular application, you cannot use that frequency cannot be used for other application, because then two subsystem or system which are using same frequency, there will be clash of frequency, and that we know as electromagnetic interference. So that aspect is looked after by WPC by not allocating same frequency for two applications, in nearby area. So keeping that in mind, you know that most useful band is starts from mid S band to X band. So that is from around 3 gigahertz to that goes up to 12 gigahertz, and this is the frequency band where the size of the component which we used to develop earlier uh, uh, used to be compared to the wavelength, and this is very useful frequency band. and that is already allocated for various applications like C-band for satellite communication, and also IMD uses that for weather radar applications. X-band is also known as a defense band, 8 to 12 gigahertz, and that is heavily crowded. Various defense system, radars, EW systems, those things use that frequency. But at the same time, you require those frequencies to be used, though those things are allocated for other applications. So keeping that in mind, that this FCC USA, they uh, I mean opened up frequency band uh, that is from 3.1 gigahertz to 10.6 gigahertz, and then allowed that frequency band with certain restriction for commercial applications. And that is how in 2002 ultra wideband frequency, which is starting from 3.1 gigahertz to 10.6 gigahertz, was made available for commercial application. Of course, lots of restrictions they have used. We will try to see that in next couple of points as a feature of ultra wideband technology. So that is the background of ultra wideband frequency range, which is made available for commercial application, while parallelly use this frequency band for defense application or various other applications. So some of the main features required for the application of ultra wideband technology, which are listed here. So as I said, that frequency band which was made available for commercial purpose is 3.1 gigahertz to 10.6 gigahertz, and here they specified that antenna which has to be used should have reasonable efficiency and should satisfy omnidirectional radiation pattern. So that was one of the rider. Second rider is that you use this frequency for very short range communication, because there was a restriction for a maximum power that can be used. And in this frequency band, it is specified the power which needs to be used is minus 41.3 dBm, with respect to milliwatt. When we take as a reference, we call that as dBm. So you can 1/10,000 lower than 1/10,000 of a milliwatt, that will be will be minus 141 minus 41.3 dBm per megahertz. So that is the specifications they put, that is the restrictions they put, so that though you are using it for short range commercial application, it will not be clashing with those conventional application which are there in this frequency band. And third criteria is that because you require for reliable reproduction of the data when you are at the receiver end, uh, uh, the system should have very large bandwidth. That was also one of the reason why this ultra wideband frequency band was released. And then it requires that very sharp pulse. Through this technology, you will be able to reproduce from at the receiving end. When you are transmitting very sharp pulse, you are able to reproduce that at the receiving end because of two reasons. That is, you ensure that distortion introduced here should be as low as possible. So there has to be very very less rise time and fall time of these sharp pulses, and also of course large frequency band. So these are the conditions based on which FCC released this ultra wideband frequency band of 3.1 gigahertz to 10.6 gigahertz. So when you using this restriction, uh, satisfying all these restrictions, when you design a system, you need to have a transmitter. If you want to reach the use the whole frequency band, you need to have a transmitter which should have a very large bandwidth. Similarly, antennas should have very large bandwidth. You require very sensitive receiver, and at the same time, uh, large bandwidth will ensure that proper reproduction of the short pulses, meaning thereby you will have large data that you will be able to transmit with fastest speed. So that will be the rider on receiver and then also processing. So designing these ultra wideband systems with all these four subsystems for large frequency band is a major challenge. So out of all these, right, we will try to concentrate in this short span of time. What are the challenges to design an antenna for such a large bandwidth, and then which are the antennas which will be suitable for that specifications. And then you have seen for antenna there is a very clear cut guidelines that it should have large bandwidth. Also, it should have reasonably omnidirectional radiation pattern so that the range coverage is large. So with these two main points, we come to the design consideration of ultra wideband antennas. You know that most of the antennas are narrow band, because almost I mean most of these antennas are resonant antenna, and when we talk about resonance, we will define that in terms of Q. So it will have frequency selectivity, and it will have a very narrow band. Like when you talk about dipole antenna, di means two, pole means there will be two polarity, and then that to separate uh, one pole which is plus to another pole which is minus, you require half wavelength. So dipole length becomes half wavelength. And similarly, monopole is a single pole, so it will have plus or minus, and then other end will be ground. So that is monopole. And you know that from your acoustic theory in the ninth standard, we have studied that between two nodes or two anti-nodes, the path length will be lambda by 2, and between node and anti-node, between two nodes or two anti-nodes, it will be lambda by 2, half wavelength, and between node and anti-node, it will be lambda by 4. That is the reason why monopole has got length as lambda by 4, whereas dipole it will be lambda by 2. So what I want to emphasize here is that when these antennas are defined in terms of wavelength, and wavelength will correspond to specific frequency. So when you move away from that frequency, criteria of half wavelength or quarter wavelength will not get satisfied, and so it will not function properly. So these resonant antennas, they are will have center frequency, and they have very narrow band. So when you talk about frequency of 3.1 to 10.6 gigahertz, even if you have a damped resonance, you won't be able to realize such a large bandwidth. You know, so that's why for these cases we don't. I mean, if you as a layman, you can visualize that it should have many resonances built in that. So the basic consideration for this type of antennas is that instead of resonance or operating frequency like I defined for the dipole or monopole, in this case we define in terms of lower band edge frequency and the total bandwidth which will be required, that is from 3.1 to 10.6 gigahertz. So we design an antenna uh, for lower range frequency, that is close to 3.1 gigahertz, and try to match the impedance. We will discuss that in detail, that we try to match the impedance so that it will have huge bandwidth. How to do that, that we'll be covering. But for the ultra wideband antennas, the basic design considerations is that instead of resonance frequency, we define lower bandage frequency and the bandwidth. And generally, all these antennas are monopole antenna, because from there only one can have omnidirectional radiation pattern in azimuthal plane. Even a dipole will have that, but then we concentrate more on monopole, because monopole has slightly higher gain, and also it is a miniaturized version of dipole. So half dipole is monopole. So most of these antennas are monopole antennas. The lower bandage frequency depends primarily on maximum height of the monopole. That I will explain. All of us, we know that, but then for the benefit of some of the students who are attending this the lecture, I will try to explain that as well. And then bandwidth of the antenna depends on these uh, that this is coined by us, depends on how impedance of various modes are matched with the feed line. So when you are feeding with that 50 ohm coaxial line, or the SMA connector or N-type connector or TNC connector, how you are able to bring the input impedance of the antenna uh, close to 50 ohm. So if you have impedance variation between 25 ohm to 100 ohm, then VSWR will be within 2, and then it will have huge bandwidth. So this mode matching concept was introduced for the first time by our group in IIT Bombay, and then I will be discussing that as well. So, as I said earlier, that cylindrical monopole antenna, and we here this length L, or we call height of the monopole, that will be lambda by 2. Just to explain in a very simplistic way, here if you see, this is the ground plane which has been shown here, and then center conductor of that coaxial connector is coming up, and then it is touching the input of this metal cylinder. So if you consider this as this is a metal cylinder, and you are exciting here this one here, the current gets set in. So all of a sudden here, that metal is getting truncated. So then beyond that, free space is there, air is there. So then you can in a very simplified way, you can consider this as open circuit, and then compared to open circuit, this one is a low impedance because we are considering this as 50, fitting at 50 ohm, and adjacent to that there is a ground plane which is zero impedance. So this is open circuit, and then you can say that this is a current minimum open circuit, and then here we are feeding and ground plane is there, current will be maximum. So then this acts like antinode, this acts like a node, and this length becomes lambda by 2. So that is what is monopole antenna. And then we know that here, that tangential component of electric field has to be zero in metal. So this field line gets truncated here, which will be perpendicular here, and then so then it will have radiation only in upper hemisphere here, and there will be that increased gain as compared to that of the monopole monopole, because all the radiation are restricted on the upper half of the ground plane, and you have almost the field will get enhanced by almost 3 dB, and your power will get enhanced by almost 6 dB. So we get increase in directivity as high as 4 to 6 dB. Ideally, it should be 6 dB. So if everything is in phase, so that is how monopole antennas are preferred over dipole antenna. It will have increased directivity, and also it is very, though it is an unbalanced structure, it is very simple to feed this structure. So this is a, conventional cylindrical monopole antenna, and functioning of this one I have just briefly explained. Now, when we try to make an antenna that which will have a larger frequency band, here this is highly resonant, and one will be able to damp that resonance by increasing the diameter of this metal cylinder, and so the bandwidth increases. Uh, uh, Nevertheless, you will not get type of bandwidth which we require for ultra wideband technology or ultra wideband application. So then this structure needs to be modified to meet the requirement of large bandwidth, retaining the basic nature of radiation of a cylindrical monopole antenna. So that is the basic design concept which is used by all ultra wideband antennas. I mean, particularly for this band, 3.1 to 10.6 gigahertz. I'm not talking about frequency independent antennas. Uh, uh, which we have those spiral antenna, or you have those low periodic antenna, and then Ramsey theory explains that how you try to define the basic structure of the antenna in terms of angle, rather than directly defining in terms of wavelength. So those things we are not discussing. We are trying to discuss about monopole antenna, so that we have omnidirectional radiation, azimuthal radiation pattern. At the same time, we have large bandwidth. Now then, we will come to these two configurations, which are the choices for ultra wideband antenna, and some of these work uh, 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 was done during my PhD time in group in IIT Bombay, and some of these concepts were introduced for the first time, though they were existing much earlier, but then we had reintroduced those concepts for designing a very uh, large bandwidth monopole antenna. So there are two choices for this type of design of these ultra wideband antenna for ultra wideband technology. Here, instead of cylindrical monopole antenna, you retain the characteristic of the monopole antenna. You take a metal strip here, and this is the length of the or height of the metal strip, and this is the width of the metal strip. So you can and then that is fed from 50 ohm coaxial connector. This is a ground plane. So this becomes then is the metal strip monopole antenna, that is known as planar monopole antenna. In this case, planar structure is square. You can have elliptical, you can have that circle, you can have hexagon, and here, I mean, this is a rectangular uh, this monopole antenna, or rectangular planar monopole antenna, and of course it is three-dimensional in the sense you have a ground plane here, and then it is standing perpendicular to the ground plane. So these antennas uh, uh, were designed way back in 1997, and then some of the early publication you can see in various literature. So here we got very large bandwidth. But how to explain the large bandwidth which was obtained, then we try to look into the basis function, and you see here that there will be fundamental mode, and then next higher mode, which you know as the next harmonics, second harmonics, will have double the frequency corresponding to the fundamental frequency, like that you have, because here basis function is sine and cosine, so harmonics will be in multiple of that fundamental frequency. So then we try to see how these impedance at various higher order modes are getting matched. That I'll come explain to you. So when we progress further, wherever you want to have some clarification, you can stop me then and there, so that I'll be able to explain to you. Because of paucity of time, I'll be rushing through the presentation. So here, this is a cylinder. This is a strip monopole antenna. The shape is square, and this is a planar geometry. We have a ground plane, and this strip is perpendicular to that, and then one will be able to design this, and that is known as planar monopole antenna. Why monopole? Because basic specification itself tells that we should have omnidirectional, near omnidirectional radiation pattern, and we have seen that this meets the requirement of that radiation pattern. Of course, bandwidth, initially we did not get large bandwidth, though the bandwidth was much higher than cylindrical monopole antenna, but then moving further, the whole frequency band was covered. So this is a three-dimensional structure. Now, having worked on this one after 5 years or so, it was thought that why not to develop these things in as a printed circuit board. So one will be able to print this square patch or rectangular patch or circular patch, elliptical patch on the dielectric substrate, and then other side of the dielectric substrate will be air. There will not be any ground plane like you have in microstrip line. That's what I was telling. These are you can say, when you are realizing this three-dimensional monopole antenna in printed form, you at best you can categorize this as printed antenna. There is no backing ground plane, which is a must for microstrip configurations. That's why I was emphasizing that this is not a microstrip antenna. It is a printed monopole antenna, or that people call, because it's only two-dimensional, so they also call this one as printed monopole antenna. And this one was known as planar monopole antenna, but then this at later stage people generalized, and then they call this also as planar monopole antenna. So you can see here there is these things in the back side. Here you have ground plane, or you did not have ground plane, you can have CPW line here. This 50 ohm will feed the input of this one, and length and width are the dimensions of this antenna. And you can see that this is the plane here. The small ground plane is printed, and this one is the monopole antenna. This is the monopole antenna, and this length, in this case, this length, here also this length, and there will be slight effect of the presence of dielectric here, and you can design this length as lambda by 4, close to lambda by 4, so that you have the lower bandage frequency, which we had defined that instead of resonant frequency, you design the antenna for lower bandage frequency and try to maximize the bandwidth by matching this one for uh, large frequency rate. So this is what is printed monopole antenna, and this is a substrate, and here the loss tangent of uh, in comparison to microstrip line, because field lines are there, only those fringing lines which are radiating, they are contributing to radiation, but those quasi TM mode feed lines will be confined between the strip and the ground plane. So there the low tangent of dielectric material plays very important role, and there will be radiation efficiency reduces drastically for microstrip antennas beyond 1.5 gigahertz if you are using a lossy glass epoxy substrate. Whereas in this case, you this backside, though there is a ground plane, but then only that much path length it will get affected, and beyond that air is there. So here the efficiency, even if when you are designing this printed monopole antenna at 10 gigahertz frequency, your radiation efficiency doesn't reduce drastically. It will be still above 80%, and then it becomes highly cost effective, because glass epoxy substrates doesn't cost much. You know about that one. So this we now onwards, we will not go back to that three-dimensional planar monopole antennas. We restrict our discussions on printed monopole antenna. So they are most sought after monopole antennas, because here you can integrate directly. You can make a transmitter here in this PCB. You can have, when you are making a system, you can have a receiver, and everything, it is a PCB integrable. You can directly feed this antenna. You can have a transmitter here itself, which you can use this printed circuit board to make that one. Filter, everything can be integrated here. So that is the advantage of this printed monopole antenna. Of course, it is two-dimensional. It is slightly compact, because you are using a dielectric material to print this strip. Circuit components can be integrated in the same PCB. That's what I was hinting at, and it is highly cost effective. So that's why these printed monopole antennas has become very popular. Uh, uh, I do not know whether I'm talking here, and then you people, whether you are listening. Sometimes the internet goes down. So am I audible to all of you?
Yes, sir, you
Yes, sir.
all.
Yes,
Yes,
sir.
yes, sir.
Okay. So this is what the features of these printed monopole antennas. The printed monopole antennas can be viewed, and now we are now explaining how this simple structure gives you such a large bandwidth. So the formulation which was proposed by us, that I'm explaining now. The printed monopole antenna can be viewed as a special case of microstrip antenna configuration. As a special case, it's not a microstrip antenna. That back plane doesn't exist in this case. So you can say that that back plane has been removed to infinity. Thereby, your thickness of the substrate becomes that much large, in a very simplistic way. That's why you get such a large bandwidth. So that was one of the preliminary explanation which was given. So that's what I am reiterating here. A special case of microstrip antenna configuration, wherein the backing ground plane is located at infinity. You have removed that. A patch is fabricated on the electric substrate, common generally FR4. Beyond the substrate, it can be assumed that a very thick air dielectric substrate, epsilon r is equal to 1, exists. It makes the microstrip antenna configuration on a thick substrate with epsilon r closer to unity, because if you average dielectric constant, if you find out the capacitance and then air gap you introduce, you will see that you will get a capacitance which will be close to or a capacity of electric field lines that will be close to that of that air. So it becomes thick substrate with epsilon r close to unity. which yields large bandwidth. That is the most simplistic explanation that was given earlier, and that had appeared in 2001. You can see those MOTL papers. Now, printed monopole antenna design, how do you find the lower bandage frequency? When you have a cylindrical monopole antenna, Balanis have given a very nice expression, which depends on the radius and then height of the monopole antenna, cylindrical monopole antenna. Now that concept has been extended, and so that resonant frequency formula was modified for various planar structure of square, rectangular, elliptical, circular, hexagonal also we introduced at later stage. So that thing was modified. So planar printed monopole antenna can be seen as a vertical monopole antenna. A monopole antenna usually consists of a vertical metal cylinder. We have seen that mounted over the ground plane, whose bandwidth increases with increase in its diameter, because lateral current will increase, and then this lambda by 4 current gets damped. There is no loss, but that gets damped, and that's why over the large frequency band it remains close to lambda by 4. So that was the concept used. A printed monopole antenna can be equated to a cylindrical monopole antenna with large effective diameter. So that is the formulation we gave. This is a cylindrical monopole antenna, and you take same height, that is the length of this rectangular printed monopole. So this height of the cylindrical monopole, if you take same as this one, and then to find out the equivalent width, you can equate here the total surface area will be 2 pi r and multiplied by this L, whereas here surface area will be W multiplied by L. So from there, you can find out what will be the width in terms of this radius. So with this most simplified concept, we gave a formulation that became accurate up to 0.2%, 0.2%. So that became the design guideline at later stage. And in the printed monopole antenna, as I was telling, you can have a different configurations. You can have square, rectangle, hexagon, triangle, circle, elliptical. Now, circle is a symmetrical configuration, so no matter from where you are feeding, that will remain circular uh, configurations. But depending upon the feed positions, you can have two different configurations for triangular patch that can be vertex fed. We will see those things. Then hexagon, you can feed at side or vertex. Rectangle, you can feed along the length, then width will become the height, or along the width when length will become the height, or you can feed at vertex. And similar these things, you can feed at vertex or any side on the these things. When feed along the vertex, then this will get rotated here. So this one will be fizzing. You will see those diagrams. Then elliptical, circular, all these things are possible here. So this is the formula which we gave, extending the formula of that Balanis for monopole antenna. That formula is the that height of the monopole antenna is given by 0.24 lambda into f, where f is radius divided by height divided by 1 plus radius divided by height. So that we modified, equating with the for the that for the square monopole antenna, uh, and or any monopole antenna, you can keep the height same as um, uh, this maximum dimension, and then find the equivalent W, and then put that formula, and it matches, and here that P is the length of that the center conductor, coaxial center conductor. And in the case of printed, uh, you can have a small factor, that K, and that you can equate as sort of effective dielectric constant, but that is not exactly equal to effective dielectric constant. You can have K that changes, depending upon what is the substrate thickness and dielectric constant you are taking. K becomes around, most of the time it lies between 1.1 to 1.2. So that much reduction in length will be there. So this is the lower bandage frequency, assuming that it is resonant at the lower bandage frequency and you design this antenna. So these are the various printed configurations which I was mentioning. The first configurations you can have here is that they are fed along the side for the square, rectangle, then rectangular along the width, but you are feeding directly the side. Here it is feeding the side, here also it is feeding the side. So 50 ohm line is directly getting truncated by larger width, so here the capacity of electric field lines will be more. So then this acts like an impedance transformer, so you, for this case, to compensate for that capacitance, you require a larger length. Whereas for these configurations, these are smoothened edge which is facing the 50 ohm line, and then here this length will transform the impedance in a smoother manner. Here it was abruptly facing, whereas here it is smoothened. And similarly, you can have that vertex fade. So here natural transition is there. You can see about the impedance. So these are the various 3 feed cases, yeah, based on this, how the input transmission, 50 ohm transmission line, which sees the geometry of these printed monopole antenna. Accordingly, one will have different that impedance transformation. So here, for this case, that if L will be same as that the height of the cylindrical monopole, only depending upon different structure, whether it's a circle, ellipse, or square, triangle, um, uh, that rectangle or hexagonal, this R will change. So based on that, equating the surface area, one can derive these expressions, for uh, for printed square monopole antenna, we can have printed rectangular monopole antennas. One can have printed triangular monopole antenna, whether you are fitting at vertex or at the side. Similarly, you can have this printed hexagonal monopole antenna. Then you can have PCMA, printed circular monopole antenna, and printed elliptical monopole antenna. So these antennas, would you remind me when 15 minutes are left? Hello.
Sir, now 20 minutes are left.
Okay, 20
You can,
minutes. So this is that impedance transformation I was talking about for the first case. That this is for the various frequency band. This is how the feed length you have to choose, and you can have for the second case, for the smoother that base or vertex, you will have this type of impedance transformation. So length of that is also the design criteria you have seen here in this equation. This is what I am indicating P, and all other parameters will be known to you. and this impedance transformer P has to be selected from. These are the closed form expressions we generated, plots, and then those things were given for the design of that. Now this gives very large bandwidth, right from 1.1 gigahertz is good sometimes for the elliptical case, for the circular printed monopolar antenna, because if you recollect, the various higher order modes are multiple of fundamental modes of function. So for this square or rectangular monopolar antenna, the modes will be equally separated. I mean double, triple, or 4 times of the fundamental frequency. But we know for the circular microstrip antenna, the roots are given by roots of the base. Various modes are given by roots of the Bessel function of first kind. So there the modes are, I mean, closely spaced. So that's why one gets, when you try to erase the impedance variation between various modes, then you will be able to realize a much larger bandwidth. So elliptical and circular microstrip antenna gives much larger bandwidth as compared to those rectangular or triangular microstrip antenna, where basis functions are sine and cosine. So that can be demonstrated using a simple example, that ultrawide band printed elliptical monopole antenna. What we did, we designed that elliptical that printed monopole antenna with a very less ellipticity here, and then uh, here in this case it will act like a very thin strip monopole antenna, and then we increased that, keeping these 2A dimension same, we increased the 2B dimension from lowest to maximum, you know so that lateral dimensions are increasing here. This is increasing, and we try to see the impedance variation in the Smith chart. You will see that this being like a strip, a thin monopole antenna, the impedance uh, uh, you know uh, variation which will be there in the, at various modes, that will be separated, and the size of that impedance, that loci will also be large. So for thin one, so you will not get larger bandwidth, but when you get the larger B here, the impedance variation between various higher order modes, that shrinks, and then that lies between 25 ohm to 100 ohm, and giving a very large impedance bandwidth, because impedance will be varying only between 25 to 100 ohm. So that can be seen here very clearly. You can see the calculated that various that modes for these things for the thin strip. You can see this is the first mode, this one the second mode, and then there will be many such modes. We have plotted only 2 modes for the thin strip. And then when your B dimension is increasing, you can see that impedance variation between these modes are reducing, and also the loop size, that is also shrinking. So if you keep increasing that B dimension for the ellipse, you can see that that impedance variation at each mode, and also between 2 modes, that shrinks, and then finally it curls around. If you design properly, it curls around the center of the Smith chart, and then corresponding that return loss plot, you can see that this is much, lower than 10 dB return loss. So that for the full frequency band, and that can be corroborated with the variation of uh, the current distribution here. This is for the first single mode, third mode, uh, that that fifth one, and then this is the seventh one. You can see there is a large variation for the first mode, but when the higher frequency for higher order modes, you can see that variation has reduced, thereby current variation is reduced. So naturally impedance variation will also reduce, and thereby you will get such a large bandwidth. You can see the bandwidth is starting from almost 1 gigahertz, and that goes up to almost here, that goes up almost up to 14 gigahertz for elliptical monopole antenna. So this is what we envisaged, and then theory and experiments that matched. And also it has got much higher efficiency. You can see here, though we use glass epoxy substrate, either at 50 even at 14 gigahertz, you can see it is around 80% aperture efficiency, and gain increases, and then it goes up to 8 dB. So this is the theory which was proposed, and you can see that azimuthal radiation pattern, though there are various modes because of the mode merging, you can see that radiation pattern in azimuthal plane still remains omnidirectional. Of course, this is a perfect omnidirectional close to fundamental frequency, and then uh, uh, it gets deformed, but it remains more or less that omnidirectional, covering the whole 360-degree. That is the requirement of these antennas. And this is the pulse width, and you can see this is a transmitted pulse, and then this is the received pulse by another identical elliptical antenna. There are less ringing, and the reproduction of the short pulse is ensured by this elliptical monopole antenna. So that was also another requirement for ultra wideband technology. Various configurations has been proposed, and here this doesn't give large frequency band because of the matching doesn't take place. If you sample of this one, then you can see that impedance variation, this is the unshampered one. You have a large impedance variation between various modes. Once you sample that, the impedance variation is restricted to 25 to 100 ohm. So you correspondingly you can see the current distribution. The current distribution becomes uniform for the sampled one because impedance is not varying, whereas here the large variations of currents are there. So these things was also explained for the first time, and one gets a very large bandwidth. This is that pentagonal. Earlier we have seen the elliptical case. We also tried the feeding at 2 or 3 different places and also displace that, so that current variation here that will be ensured that that remains uniform, thereby your impedance variation is minimum. This is dual polarized, which was proposed. You can have why dual polarized? Because it will have 2 components, and of course, it will give large bandwidth when we match these things. This is again, this is one vertical polarized. This is horizontal polarized. So it becomes dual polarized over the large frequency band. So all these things were done, all different configurations that has been given, and then using the same resonant frequency formula for the lower bandage, and then that increasing the lateral dimension, one will have less variation of impedance between various modes, thereby leading to you can say multi-octave bandwidth, ultra wide bandwidth. Different configurations were tried. Then there were also requirement because 3.1 to 10.6 gigahertz, some frequency bands are to be avoided. For that, you can have different band notch configuration. So this will give band notch or lower frequency because of larger length. It will give a higher frequency. So all these things one can have. The slot one will be able to cut. You can have a. I'll conclude in 2 minutes or 1 minute. We can have a slot that will resonate and then so mismatch at the frequency where we don't want it to radiate. So band nodes can be created by slots, uh, by a different resonating structure, or introducing a mismatch at the input at that particular frequency. Again, resonance structures one uses, and then the node and antinode concept, whatever we have studied in 90 standard, those things can be used for this one, and different various configurations are there. People have come up with various configurations, and one can have a band nodes as well. So to conclude this one, I say that these are the printed antennas. They are not microstrip antenna, and their structure is so designed, basically equivalent. They are equivalent of the cylindrical monopole antenna. When the height of the cylindrical monopole antenna is taken as the height of that printed antenna, and calculating the equivalence and uh, uh, design at the lower bandage frequency, and because of the increased lateral dimension, the lateral current flows, and that in turn leads to that less impedance variation at various modes and also in between various modes. So it gives very large frequency band. And I would like those people who are working on ultra wideband antenna to at least see one paper which was published in 1998, and that has been used extensively. This one, 1998, and this has over 1,000 citation. This one. NP Agrawal was BTech students in IIT Bombay. Of course, I did PhD with Professor Girish Kumar. So we formulated this one, and one can use as a starting point if someone is taking up this topic, reading this paper. It's a very short paper. So I'll end here. I mean, I will take up questions if time permits.
Thank you, sir. If anyone have any question, please go ahead.
In the message box, there is some question.
Hello.
Madam, may I go ahead with the questions?
Question?
Okay. Good afternoon, sir, and good evening.
Obviously.
Thank you for this wonderful presentation and in-depth knowledge that you have provided. I have a few questions on your presentation. Actually, some are already answered or half answered, and some are beyond your presentation. If we use a signal of large bandwidth, so generally it is said in the literature that it is very easy to resolve signal components at the receiver if the signal bandwidth is very large. So my question to you is,
Yes.
what is the relationship between this signal bandwidth and the resolution that is received at the receiver? Why is it easy to resolve these signal components?
See, if from Fourier transform that the short pulse will cover the large frequency range in frequency domain, isn't it? So
Yes, sir.
the answer lies there. If you have large bandwidth, then you will be able to have a very sharp resolution in time domain. This is what they mean by that.
Okay, okay, okay. And sir, one last question. Sir, I am recently working with ultra-wideband MIMO antennas,
Yes.
and I want to know their practical applications.
See that to have effective communication, people are going for MIMO antennas, so that you are able to send large amount of signal, uh, like that in a space, that polarization, diversity, and all these things are being used in MIMO antenna. So let us say you have a rectangular patch, and then you can have two orthogonal this can be excited, so you will be able to send double the data. You are using polarization, orthogonality of this one. So MIMO antennas has got huge potentials in future, so that you will be able to send a large data. So people have gone up to, I think, 12 output, single input, 12 output, multiple input, multiple output also uh, has been employed. So it has got lots of future applications.
Okay, thank you, sir.
Sir, there is another question from Tirumala Krishna.
Yeah.
So the question she had written that how the antenna design is valid without any design equation. He wrote the
No
question
design
in the chat
equation.
box.
No, I did not get the question. Yeah, tell me.
Sir, it is written in the chat box.
To avoid an infinity mirror, don't share your entire screen, or no, there is no question here. I'm not able to see the chat box. You can ask me what is the question. No, no, unless you do calculate. See, I mean, these days, because of simulators are available, people directly go learn simulation tools and try to cut and here and there and try to see the response. But during our time, we had to write the equation. From the equation, we used to write a MATLAB program or Fortran program and used to do that. So the formulas have to be used first to get a proper insight. So that is why that lower bandage frequency formula was derived, and then how the modes are varying. What will be the various modes for in the rectangular patch, what are the various higher order modes for the circular patch. All those things needs to be calculated, and then you see whatever surface current calculations I have seen, that was done only 6 years back, but during our time those things were not available. So one doesn't get insight by just going and drawing some configurations and cutting here and there and getting the response, unless you do preliminary calculation first and then design that in your simulator, that configurations, and then do optimization using software. uh, See, I'll give you the example. If you have to band notch, you have to design a band notch, so then you cut a slot, let us say. That slot is inside the metal patch, and you have cut a slot. Now you cannot just take any length of the slot. Of course, you keep varying and then finally you will get the right length. But if you know the theory of the slot, how it works, how slot works, both end of the slot are sorted by the metal. So there, that is a current maxima, other end also current maxima, and between two current maxima there has to be a current minima. So at two ends of the slot you have short circuit. At the center, though you don't have open, but then center of that slot will be open circuit, you know. So then if you know at the required frequency you have to cut a slot, then you need not go to the simulation and the try iteration. You directly use a formula of lambda g by 2, because dielectric will be there, you are printing metal on the dielectric. So lambda g will be, you can take lambda g with that effective dielectric constant formulation I mentioned earlier, and then you take lambda by 2, so that slot will resonate at that particular frequency, so that that is resonant, and that will provide if you are cutting a slot at the feed line, then that will provide that short circuit, and then all the power will be reflected back and nothing will go to the patch and get radiated. So